Okay, so the next person that we talked about was Harry Hess, and he and his colleagues' idea of seafloor spreading. There are maybe four people that we talk about in most intro geo classes. It's Alfred Wegener and Arthur Holmes. This guy Harry Hess and kind of the father of modern geology, a worker named James Hutton. And we'll talk about him when we talk about relative ages of events and rocks. But seafloor spreading was really pioneered in the 1960s, the early 1960s, late 50s. It really was kind of cemented with this paper that I mentioned in 1963. But what it says is that perhaps Arthur Holmes was right. So if we go to this PowerPoint here, perhaps Arthur Holmes was right, and there is mantle convection. If we were to draw that in on the iPad and throw it in there, there's some convection in the upper mantle, this region of the mantle that we refer to as the asthenosphere. That is just this upper zone of the mantle that's capable of flow. It's not a liquid, it's a solid, but it's capable of flowing. It's kind of a plastic solid that flows over time because it's very hot and it's under a lot of pressure. Okay, and what seafloor spreading says is that perhaps there is convection in the mantle, and that creates upwelling zones of hot material. Like you can see in this figure down here, hot materials rising in convection cells, and it's creating a zone of really hot material, and these convection cells are pushing the material on either side in either direction. Okay, and so you could see that in the iPad in a variety of places where there's upwelling of hot material and downwelling of cool material. And this really came out of a couple of observations. In particular, the fact that there are these peculiar mountain range looking features on the seafloor that extend almost across the entire Earth. The Mid-Atlantic Ridge extends basically the entire it's an entire hemisphere, a continuous ridge that's much shallower. It's about 2,000 meters shallower than the ocean floor surrounding it. So that's really strange. It requires some very large scale process to explain that. Similarly, there are these very deep areas that are near some of the continents, but not all of the continents. Some of the continents have an edge that gets, down to about 10,000 meters, really, really deep, compared to the vast majority of the ocean floor, which is about 5,000 meters. So this is a strange observation that Harry Hess and his colleagues were kind of struggling with. They also observe other features like these volcanic arcs or chains of volcanoes that seem to run directly parallel but offset from those very deep trenches. That's a very strange observation that requires, again, some large-scale process to explain. And so what they came up with was seafloor spreading, and that is this notion that new ocean crust is being produced at these mid-ocean ridges, these what we call spreading centers. And the spreading refers to the fact that the plate, the actual tectonic plate here on either side, is spreading apart from that ridge, right? And it's being driven along by these mantle convection currents that Arthur Holmes initially proposed. And so on the iPad there, if we draw in some crust, it might look something like this, right? So you have lots of areas where there's, this is a mid-ocean ridge. There's hot material coming up to the surface, creating new ocean floor, which is this thick black line there. And it gets transported laterally. We encounter a continent there, right? There are not plate boundaries on those continental margins, that one, right? It just goes from continent into the ocean. We can draw in the ocean there. That might make it clearer, right? We have a continent and the ocean. There's no plate boundary there. We could get rid of those arrows, may as well. You could leave the magnetic field just for fun. So you transition from a continent onto ocean crust without crossing a plate boundary. That's what we call a passive margin. Okay, that's in contrast to an active margin. Here's an active margin, right? We have a mid-ocean ridge that's creating new ocean crust. That lithospheric plate is riding along and then being subducted beneath a continent. And above the subducting slab, there is a volcano. If you looked in 3 dimensions, it would look something like this block diagram beneath my camera here. There would be a chain of volcanoes rather than just a single volcano, because we're just looking at a 2-dimensional cross section, right? Okay. And so, this is a really profound revelation for geology as a whole, right? We can explain a ton of different things that we otherwise couldn't have prior to this discovery. And so we talked about a few of those, but the real supporting evidence for this, the first kind of indisputable evidence, came from paleomagnetism, and it reflects the fact that ocean crust is made up of basaltic composition, and that is a mafic composition for a rock. It has a lot of iron and a lot of magnesium, and the combination of a continuous production at mid-ocean ridges of mafic rocks gives you a continuous record of iron-bearing minerals that preserve the magnetic field that was present when the rock cooled, okay, when it was created. And so the ocean floor reflects just this continuous barcode of reversals in the magnetic field that occur periodically, right, that you guys looked at for your homework. And so it not only predicts that record would exist on one side of the mid-ocean ridge, but that it would be roughly symmetrical around the mid-ocean ridge. And indeed, that is what we find. It's shown in this cartoon below me. It looks like a barcode, and it's symmetrical, and that reflects those processes. It's impossible to explain otherwise, I would say.